Hello, this is Richard Rood, and this is a module in my course on climate change and climate change problem solving. The subject of this module is Earth's energy balance. In this module, we will do an accounting of the energy balance. We will use the conservation principle, which is the primary principle on which climate science is based, and we will make a budget calculation. What we will see is that energy from the sun can be absorbed or it can be reflected. And if it is absorbed within the earth, then the energy can move around. And one way that energy moves around is by weather. We will look at this figure and another updated version of this figure. This is a figure of the radiation balance. It comes from a paper in 1997 by Jeff Keel and Kevin Trenberth. And the basic idea of the figure is that energy comes in from the sun, and that energy can go several places, which we will look at in far more detail. And then the energy goes out over here as long wave radiation. Since we are interested in a perspective or point of view of being at the surface, we will be especially interested in this energy that is absorbed at the surface and how it moves around or is redistributed. What I want to do in this module is essentially to build up this picture. I want to follow the energy through the Earth's climate. In order to do this, we're going to think of our system, of our Sun-Earth system. And we're going to start by what happens with the energy that comes from the sun. Energy is coming from the sun, and two things can happen. It can be reflected or it can be absorbed. We also have the atmosphere, and like the surface, the atmosphere can reflect or it can absorb energy. In the atmosphere, there are clouds which reflect a lot and absorb some as well. So we see that this energy that comes from the earth, there are two basic things that can happen to it, absorption and reflection, but we see that the absorption of energy can occur at the surface, in the atmosphere, with clouds, and so you start to see the complexity that evolves within the Earth system. For convenience, I'm going to hide the sunbeam and the reflected solar over in RS, over here in this part. So here's the sun, and what we've done is we've removed this sunbeam from the figure, and we've left the parts where the energy is being absorbed at the surface, in the atmosphere, and in the clouds. If we consider only the energy that has been absorbed, what happens to it? First, we could think of it as being converted from this solar radiative energy, which was primarily in the visible, though the spectrum is much broader than the visual part of the spectrum, but it's primarily in the visual, and it's converted to thermal energy. That is, it heats up the places where it's absorbed. We are generally familiar with the idea that heated molecules emit energy in the infrared radiation. So we have essentially the conversion from visible to infrared radiation. It's then going to be redistributed by the ocean, the atmosphere, land, ice, life. What we know is that the energy that is absorbed primarily in the equatorial or tropical regions ends up being redistributed much more equitably around the planet as a whole. That is, it's transferred from the tropics up to the polar regions, and that transfer is primarily through the atmosphere and the ocean. So the terrestrial energy ends up into three reservoirs. One of them is radiative energy, the infrared or thermal energy. One of them is the phase transition of water, and one of them is just simply warm air and thermals. The phase transition of water is very important to our climate, as our climate And our society has evolved with a balance of liquid water, water vapor, and ice. And that balance of really how much, say, might be in ice is really a measure of our climate and sort of the mean temperature of the Earth. And it, of course, has consequences about sea level and other attributes of the climate. But it takes heat to turn ice to water and water to steam, that is, vapor. And when there's a conversion back, it releases heat. So water itself, and rain even, becomes essentially another reservoir or form of energy. So we have the infrared coming back up into the atmosphere. We have the latent heat that's coming back up and leading to clouds, and this is a representation of precipitation. And then we just have this thermal energy, hot air rising, coming up into the atmosphere. We already see the role of clouds showing up here in a couple of ways. One is as this physical process associated with phase changes, and the other is it's going to have important effects itself in its ability to absorb infrared or thermal energy. So the infrared radiation is going to get more and more complicated. Some of it goes straight to space. Some of it is absorbed by the atmosphere and re-emitted downwards. And some of it is absorbed by clouds and re-emitted downwards. Some of it is absorbed by clouds in the atmosphere and re-emitted upwards. So what you can see is that this radiation that's coming from the surface is got some going up and all the way out to space, some circulating back between the atmosphere and the surface again, and then to be re-emitted and go back to space. Some of it goes up to the clouds and comes back to the surface again. And over time, it is transferred from layer to layer in the atmosphere, and again, some goes back out to space. So what happens if we make this atmospheric blanket thicker? The way we are, in fact, mostly doing that is through the addition of carbon dioxide, which is one of the gases that absorbs infrared radiation and then re-emits it both downward and upward. If we just think about the infrared radiation and forget about the clouds for a while, then if we make the blanket thicker, more energy is held down here and it becomes warmer. Less energy is held up here, or less energy is up here, I should say, because that energy is being held down to the ground. So we start to see a cooling effect up here at higher altitudes. This is paradoxical to some, that in a warming Earth we would also see signals that are cooling. But that is because of the basic physics of radiative transfer, the conservation of energy, and the attributes of fluids such as air, which has a strong relationship between density, temperature, and pressure. If we add more atmosphere, make it thicker, then the part down here will get warmer still. And if we continue on here, it will get cooler still. So we will see a change in what we often call the lapse rate, or essentially the vertical distribution of temperature. It'll become warmer at the surface, it'll become cooler up high. So the addition of greenhouse gases to the atmosphere causes this warming near the surface and colder in the upper atmosphere, and this is part of a fingerprint of greenhouse gas warming. There could be multiple ways in which the climate warms, and so it is important to identify characteristics of different mechanisms of warming so that we can ultimately do an attribution of what is causing the warming. And we do that through a process called fingerprinting. If we think about a couple of details of emission, then there is an atmospheric window through which infrared or thermal radiation goes straight to space, and there's a water vapor window. The carbon dioxide window is often said to be saturated. This does not mean that CO2 is no longer able to absorb infrared radiation. What it means is that it takes longer and longer to get to space. So this would be like putting on extra blankets. It just takes longer for you to become cool if you have extra blankets on you. If we think about the greenhouse gases and we think about the atmospheric windows, then we start to appreciate that new greenhouse gases like N2O, nitrous oxide, the chlorofluorocarbons, and methane closes windows that are presently open. And this is one of the reasons that they have a stronger molecule by molecule effect than, say, additional carbon dioxide. Is because presently there are places that energy can escape out of the earth and go to space. And we will be closing windows by adding these new gases. Additional CO2 makes the insulation around the window tighter, is what I would like to say, because those windows are already pretty much saturated and closed. So what matters? As we start to think about how energy gets to the earth and then becomes trapped by the atmosphere to warm the surface, then we have things that change absorption, have an impact on the energy balance. So some of it is absorbed by the atmosphere, some is absorbed by the surface. And if you think about things at the surface that change absorption, the easy one that people are generally familiar with is a white surface versus a black surface. A white surface reflects, a black surface absorbs. A big difference in the Earth system is between the land and the ocean, where the ocean, because it's also a fluid and has a lot of heat capacity, can absorb energy and then take it down into the ocean and increase its heat content. So the ocean can absorb a lot of energy and hold it, but it doesn't just hold it, it also releases it back into the atmosphere. The other thing that we have are things that change reflection. So clouds are very strong reflectors, and therefore, if we can change the clouds, we change reflectors. And then again, at the surface, if it's shiny and white like ice, or if it's darker like the ocean, again, we have ways that we change reflection there. The climate could also change by changes in the sun. And it can change by how energy is transported down from the surface and into the earth. So what we're doing with the carbon dioxide global warming problem is we are changing things that change absorption. We are changing what is going on in the atmosphere, and essentially this return here between the atmosphere and the surface of this infrared radiation. If we were to start to think about the problem of how do we perhaps intervene and change the climate, then we get back to this idea of we change something that changes reflection or something that changes the absorption. That's generally the way we think about climate interventions, which have been called in the past geoengineering. If you want to think about how to quantify this, and you think about linking it back to a model so that we can both diagnose and predict what might happen to the climate, energy reflected is equal to the fraction of the total energy reflected times the total energy. This fraction of the total energy reflected is called the albedo. Energy absorbed is then simply the total energy minus the energy reflected. So it's 1 minus this fraction, the albedo, times the total energy. The fraction of total energy reflected is strongly related to clouds, ice, ocean, trees, and the other characteristics of the surface of the Earth. If we look at this figure, the original figure from the 1997 paper by Keel and Trenberth, you will see that the numbers up here, 342 coming in, and then 107 reflected, and 235 going out as infrared or long wave radiation, then you'll see that those numbers add up, and in this figure, N equals out. I'd also like to note that in this figure, this number down here is that the surface is quite warm and causes this radiation that goes back up here, 350, which is actually larger than what's coming in. So that's where you're starting to see the greenhouse effect, because it goes up, it comes down. So you can see that 324 of this is coming back down. So there's a sort of cycle here of energy going up and down and staying here and being held here a while, which has its impacts on life, but it's also giving it time to be absorbed by the ocean or to melt ice. So here's the new figure, the update in 2009. And what's important to notice in this figure is that what goes out does not equal to what's going in. There is a net absorption at this point. So this is 341, slightly different number than in the previous figure because of our improvement in observations. This is 102 being reflected back out, and 239 going up. So if you add those two together, of the 9, 10, 11, 341, and look at the more precise version here of 341.3 and 238.5, we see that there's now a net absorption of about 0.9 watts per meter squared. So one of the things I would like to point out, again, is the cycling of energy over here, which is the greenhouse effect. And what we're doing is we're modifying the greenhouse gases, which are responsible for this sort of return energy circuit here. So in summary, energy comes from the sun, it's sent back to space. You can reduce your thinking to what happens to this energy, or things that absorb it, things that reflect it, and then we get energy moving around, which we have not really talked about in this module. We store the energy at the surface of the Earth. Oceans pick it up and hold it longer. Ice takes it up and melts. And that balance between solid, liquid, and gaseous or vapor water is changed. Thank you.